Thank you very much. Good afternoon, everybody. Hello again. So this afternoon, my talk is really switching away from the moon, but looking at asteroid rendezvous. And I'm very excited to be able to present you the results of a study we just completed in our concurrent design facility at ESA ESTEC on this mission and system concept called M-ARGO. And I'm presenting actually on behalf of my colleagues, all of my colleagues that presented in or participated in the CDF study, and also my colleagues in the Science Directorate, Detlef Koschny and Cristina Bramanti, who were looking at the science and instrumentation aspects. So, as I said, it's a study we just completed, so this is the first time I've presented the concept to a public audience. And the origins of it really go back to the past studies and ongoing ones that we have been doing for deep space CubeSats. You probably, if you were here last year, remember the CubeSats on the Asteroid Impact Mission, and that was something that was completed in another cisnova. Of course, you probably are aware that the AIM mission itself didn't get the funding needed to go forward in our ministerial council. But out of adversity come some interesting ideas, I think. So actually that loss of funding led us to think, could we actually get to an asteroid with a CubeSat without having to rely on a larger mother craft? So that's really where we started from in the study, and we made all the trade-offs and analysis to lead to a result which I'll present now. Of course, we also have the LUCE concepts, which I presented this morning in 2 talks. All of these, of course, are mother-daughter architectures, and what we're looking at in terms of M-ARGO is a complete standalone system. So, get launched on a piggyback launch, near-Earth escape. Can you go to an asteroid? It's a big challenge, I have to say, and we were able to come up with some good solutions to the challenges. Overall, I would say standalone deep space CubeSats, they do have a very high potential, so it is worth looking at this clearly. I don't have to tell you that. But we believe there is a high potential to cut the entry-level costs of deep space exploration by about an order of magnitude. As CubeSats have done in low Earth orbit, they've lowered the entry level to LEO for many actors and bringing new actors into the space domain. Could we do the same thing for deep space? One thing which became immediately obvious was if you start in LEO, GTO, or somewhere in Earth's gravity well, you have to spend a lot of delta V, of course, and a lot of propellant just to get out into deep space. So we looked at just circumventing that and looked at piggyback launch options to near-Earth escape. So primarily translunar injection, injection onto a transfer trajectory to Sun-Earth L1 or L2, or out-of-planet missions, of course, which are executing several swing-by maneuvers to the Earth, Mars, Venus, and so on. So not actually piggybacking on large missions in terms of interfacing with the spacecraft, but actually interfacing with the launch vehicle at the stage deploying those large missions. We looked at what you could do with a 12U CubeSat. The trade-offs we did included 6 views to constraining what we wanted to do. So we started with a 12U CubeSat constraint, and in order to actually rendezvous with asteroids, of course, one needs to overcome the challenges of propulsion. We looked there at high specific impulse electric propulsion systems. And of course, when you're out in deep space and you need to detangle your spacecraft, there's no nice magnetic field there to do that too. So we looked into also cold gas RCS. These are really enabling technologies for standalone deep space CubeSats, as is deep space transponder. You have to have a high gain antenna to get any kind of reasonable data rate back to Earth for the payload data, but also TMTC as well. Powering the propulsion and the transponder, they both need high power. So we also need to generate that power on board to deliver. So another enabling technology we looked at was deployable steerable solar arrays in order to get that power in. And we shouldn't forget, even with the 12U CubeSat volume is very constrained, so we looked at also highly integrated radar avionics as well. Potential missions, our primary scope, it's a technology reference study, so we don't go top down from mission objectives to system design. We look at what you can do with the technology. So the main mission profile we looked at was the rendezvous for physical characterization, the science and resource evaluation, prospecting. We looked at also an alternative mission profile, which I'll come on to at the end, which was actually going to Sun Earth L5 launch point for space weather monitoring, giving some advanced warning of solar storms. So this was done in the CDF, and our primary mission goal, let's say, was to rendezvous with an asteroid. That was the main objective. Once there, characterize the physical properties of it, the shape, the surface model, the mass, and therefore also the density, and also to assess the potential of resources exploitation, so looking at the composition and hydration aspects. The mission phases then, our baseline, after a few trade-offs, our baseline for the piggyback launch was to be injected onto a Sun L2 transfer on the launch for a large astronomy mission. At ESA we have a few of these in the pipeline, including Euclid, you may know, which is going to L2 2022 timeframe. After the injection, detumble, transfer to a halo orbit, an L2, and simply park there and wait for the optimal transfer to the asteroid target. So then, after departing L2, doing the transfer with low thrust solar electric propulsion, we concluded you can't really do a rendezvous with chemical propulsion, so EP was the critical one. Actually, at the asteroid, do a 6 months phase of close proximity operations, observing the asteroid remotely using remote sensing instrumentation. For the comms, you really do need to have large ground station antennae, you probably realise. We looked at how to utilise our large ground stations in the ESTEC network, 15 metres and 35 metres. And there also is a large 64-metre radio telescope in Sardinia, which could be repurposed to receive signals in the X-band. So we had a look at what we could do with that as well for the payload data. And then the usual architecture for the ground segment, like a modern ESOC, and it's essential actually to have flight dynamics support also. Our objective was to have a first mission, including the non-recurring costs of less than 25 million euros cost, and to actually be ready for a launch by 2020. Just giving you a system overview then, as I said, 12U form factor. We're actually, we decided to dedicate 1U for the payload out of that 12U. Most of the rest of the spacecraft gets taken up by propulsion and comms equipment, about 8 units for the EP system, more or less, including our baseline system, which we selected, was the micro-gridded ion engine running xenon propellant. We've got 2 cylindrical xenon tanks storing about 2.8 kilograms of xenon at 60-70 bar. The system also includes gimbal on the thruster to minimize torques and reaction wheel offloading. PPU, of course, the power processing unit, and the usual neutralizer. For communications, with baseline X-band, deep space transponder with ranging and Doppler capabilities, 3 output channels and 2 receive channels, 4 patch antennas for omnidirectional coverage for TT&C, and a deployable reflector array high gain antenna for the payload data transmission. Both of those subsystems need a lot of power, so we've come up with a design with 2 deployable wings. steered with one solar array drive mechanism. And we've actually, for each wing, we looked at two options. 3 panels per wing or 4 panels per wing, so 6 or 8 panels in total. And you can see here we're able to put into the electric propulsion at least at 1 AU distance from the Sun, 93 watts with the 6 panels and 120 watts with the 8 panels. And that equates to about 1.7 millinewtons and 3,000 seconds of ISP from the propulsion. Overall, the vehicle mass we come out with is around 22 kilograms, so not a great difference for both options. For AOCS, basically we need to have some navigation, of course, particularly relative to the asteroids. We have a VisNav cam, star tracker, and sun sensors with an IMU. There's not a lot of redundancy, so we weren't able to get the usual 4 reaction wheels in for the moment, but at least 3 reaction wheels and 8 xenon cold gas reaction control thrusters. And then we've got the modularized, highly integrated avionics, which is also doing some payload data processing. Thermal control turned out to be quite a challenge, I have to say, during the study. But we came up with a passive solution with radiators to deep space with heaters for the cold phases of the mission. But the main problem, I would say, was actually dissipating the excess heat power from the propulsion system and the deep space transponder. They're not used simultaneously, but even so, it's still quite a challenge. So this is what it looks like. You can see here the spacecraft configuration. We've got the rear line engine there, 2 patches. You've got the reflector array antenna, which is also technology we have under development in Europe, plus the 6 panel options for the solar array. Payload we selected for physical characterization was the multispectral imager. That's based on the Aspect instrument, which is developed in Finland by VTT Research Centre. We're flying an early version of this on our Picasso CubeSat in low Earth orbit, and this is to be extended into the near-infrared and SWIR channels for deep space, and it was one that was previously studied for the Europeans study. Overall, I won't go into too much detail, but overall, at the kind of close proximity distances to the asteroid, which is about 500 meters, we get a resolution on the surface of around 9 to 44, well, 9 centimeters to 18 centimeters. For the visit near, there's only one channel for the SWIR, so it's just providing spectroscopic measurements. We also managed to fit in a laser altimeter, so there is quite a nice unit developed by Geophysical in Germany. It's only 33 grams of mass, and it's very compact, of course, and this is very useful for the radio science, the gravity field determination in conjunction with the radio science, which we're going to conduct. Just to say that we looked at different targets. We used the whole NEO database, 700,000 objects, and with our low thrust trajectory codes, with the constraints we placed on the masses, we came up with about 30 objects that could be rendezvous with this kind of system design with a propellant mass of less than 2.5 kilograms. Those 30 targets, we also then progressed further into a more detailed trajectory analysis, because we have to take into account the variability of thrust and specific impulse with solar distance, and that turns out to be very important for asteroid rendezvous. We've got quite a range of solar distances. So we put together our sunbeam to iron beam optimization, trying to minimize losses and maximize the power into the EP system to maximize thrust. And we actually then focused on 7 different targets out of that list of 30. We actually ruled out 3, including York. Unfortunately, that would have been a fantastic science target to visit. But actually, we have detailed feasible trajectories for now 4 targets, and they are all actually at the point of close proximity operation. less than 1 AU distance from Earth, so it's quite convenient for the close proximity operations. I won't go into details about the mission analysis, but just to say our colleagues at ESOC have done an outstanding job to look at the transfer trajectories. All of those targets are very faint targets, which means they're something below 50 meters. And this turns out to be very scientifically interesting. All of the asteroids we've visited so far are larger than about 300 meters. And as was shown this morning, this nice chart, when you have smaller objects, you have faster rotation periods. So probably not rubble piles and more monolithic bodies. These are totally new bodies that we haven't visited yet. So it will be actually new science. Close proximity operations, of course, the 50-meter asteroid, the gravity field is not very significant, but we basically opted for a square pattern, 7-day repeat cycle, close proximity operations, which is quite convenient for operations costs purposes. But you can see here that for a particular target, UV136, we're going around 300 to 500 meters away in a square, so that the left-hand figure is the sun looking at the projection of the asteroid, and that's the side view from the ecliptic there. So these types of trajectories are possible also to achieve radio science as well. On the communications side, we're looking quite good on performance there. At 1 AU distance from Earth with a 15 watts RF power back to our 35 meter station in ESTEC, we've got 7 kilobits per second, and back to the Large Radio Telescope, it's about 25 kilobits per second, which turns out to be around 10 to 100 gigabits of information over a 6-month mission. Then there was the alternative space weather mission. I don't go into too much details here, but there we swapped out the payload for a radiation monitor and a magnetometer, take observations, a 20-month transfer, and that's all within the capabilities of the system design. So just to conclude, based on our study, we believe that standalone deep space CubeSats are technically feasible in the near term, with some technology developments. The critical ones are on the solar array drive motor, the propulsion, and the X-band transponder. They're around TRL 3 to 4 at the moment. We have a plan in our technology program to take these up to TRL 6. Once those developments are started, we've identified a piggyback launch to L2. Then we can actually start with this M-ARGO mission, phase 2B. Our conclusion is on the cost side that it's marginally feasible within the 25 million budget. It turned out that actually a major cost driver for that budget was flight dynamics costs. So apparently flight dynamics costs are not scalable with spacecraft size, of course, and we are now going to start investigating lower cost approaches for deep space navigation and flight dynamics to try and reduce the budget even further. We believe it's feasible to launch the mission by 2021. And going along the way, there will need to be some radiation harmless assurance on the COTS electronics, of course, that was well covered. So the next steps, technology development, flight opportunity, basically. Thank you.
Time for one question.
Very interesting talk. I have many questions, but I will try to limit it to one. What if we raise the bar further and we aim to, for instance, Mars and direct escape without being injected into an escape orbit? Would that be feasible according to you? Or?
It would be feasible. The main point here, though, is this slide. It doesn't actually extend beyond 1.2 AU here, but we have graphs to 1.5 AU. Even with the 8 panels option, the thrust is going to be very low because, of course, the solar power drops off whenever elsewhere. So it's mainly a matter of having enough thrust for Mars insertion. and also then spiraling down to wherever you would want to go. So the spiral down to Mars would take quite a long time from the point of view of the low thrust again. But I don't see it in the future.
I think that's all we have time for, but join me again in thanking Roger.